In probability theory and statistics, the gamma distribution is a two-parameter family of continuous probability distributions. The common exponential distribution and chi-squared distribution are special cases of the gamma distribution. There are three different parametrizations in common use, with a shape parameter k and a scale parameter I. With a shape parameter I plus or minus a equals a k and an inverse scale parameter I squared a equals a1/I, called a rate parameter. With a shape parameter k and a mean parameter I1/4 equals ki squared. In each of these three forms, both parameters are positive real numbers. The parameterization with k and I appears to be more common in econometrics and certain other applied fields, where for example the gamma distribution is frequently used to model waiting times. For instance, in life testing, the waiting time until death is a random variable that is frequently modeled with a gamma distribution. The parameterization with I plus or minus and I squared is more common in Bayesian statistics, where the gamma distribution is used as a conjugate prior distribution for various types of inverse scale parameters, such as the I of an exponential distribution or a Poisson distribution or for that matter, the I squared of the gamma distribution itself. If k is an integer, then the distribution represents an Elang distribution. That is, the sum of k independent exponentially distributed random variables, each of which has a mean of I. The gamma distribution is the maximum entropy probability distribution for a random variable x for which E, x, equals key equals I plus or minus /I squared is fixed and greater than 0, and E, ln, x, equals I, k, plus ln, I, equals I plus or minus ln, I squared is fixed. Characterization using shape k and scale I. A random variable x that is gamma distributed with shape k and scale I is denoted. Probability density function. The probability density function using the shape scale parametrization is. Here I, k, is the gamma function evaluated at k. Cumulative distribution function. The cumulative distribution function is the regularized gamma function. Where I cubed, k, xi, is the lower incomplete gamma function. It can also be expressed as follows, if k is a positive integer. Characterization using shape I plus or minus and rate I squared. Alternatively, the gamma distribution can be parameterized in terms of a shape parameter I plus or minus a equals a k and an inverse scale parameter I squared a equals 1/I, called a rate parameter. A random variable x that is gamma distributed with shape I plus or minus and rate I squared is denoted. Probability density function. The corresponding density function in the shape rate parametrization is. Both parametrizations are common because either can be more convenient depending on the situation. Cumulative distribution function. The cumulative distribution function is the regularized gamma function. Where I cubed, I plus or minus, I squared x, is the lower incomplete gamma function. If I plus or minus is a positive integer, the cumulative distribution function has the following series expansion. Properties, skewness. The skewness is equal to, it depends only on the shape parameter and approaches a normal distribution when k is large. Median calculation. Unlike the mode and the mean which are readily calculable formulas based on the parameters, the median does not have an easy closed-form equation. The median for this distribution is defined as the value I1/2 such that a formula for approximating the median for any gamma distribution, when the mean is known, has been derived based on the fact that the ratio I1/4/I1/4 a I1/2 is approximately a linear function of k when Ka per mil 1 yen. The approximation formula is: where is the mean? Summation, if xi has a gamma, key, I, distribution for E equals A1, A2, A, n, then. Provided all xi are independent. For the cases where the xi are independent but have different scale parameters, see Mathau and Moskopoulos. The gamma distribution exhibits infinite divisibility. Scaling, if. Then for any Ka A0. Hence the use of the term scale parameter to describe I. Equivalently, if. Then for any Ka A0. Hence the use of the term inverse scale parameter to describe I squared. Exponential family. The gamma distribution is a two-parameter exponential family with natural parameters k(a1) and a1/i, and natural statistics x and ln, x. If the shape parameter k is held fixed, the resulting one-parameter family of distributions is a natural exponential family. Logarithmic expectation, one can show that. Or equivalently. Whereas the digamma function. This can be derived using the exponential family formula for the moment-generating function of the sufficient statistic, because one of the sufficient statistics of the gamma distribution is ln, x. Information entropy. The information entropy is. In the K-I parameterization, the information entropy is given by Kullbacher-Leibler divergence. The Kullbacher-Leibler divergence, as with the information entropy and various other theoretical properties, are more commonly seen using the I plus or minus I squared parameterization because of their uses in Bayesian and other theoretical statistics frameworks. The KL divergence of gamma, I plus or minus p, I squared p, from gamma, I plus or minus q, I squared q, is given by. Written using the K-I parameterization, the KL divergence of gamma, Kp, Ip, from gamma, Kq, Iq, is given by. Laplace transform. The Laplace transform of the gamma PDF is. Differential equation. Parameter estimation, maximum likelihood estimation, the likelihood function for n-iod observations is. From which we calculate the log likelihood function. Finding the maximum with respect to I by taking the derivative and setting it equal to 0 yields the maximum likelihood estimator of the I parameter. Substituting this into the log likelihood function gives. Finding the maximum with respect to k by taking the derivative and setting it equal to 0 yields. There is no closed-form solution for k. The function is numerically very well behaved, so if a numerical solution is desired, it can be found using, for example, Newton's method. An initial value of k can be found either using the method of moments, or using the approximation. If we let, then k is approximately, which is within 1.5% of the correct value. An explicit form for the Newton-Raphson update of this initial guess is Bayesian minimum mean squared error, with known k and unknown I. The posterior density function for theta is. Denoting. Integration over I can be carried out using a change of variables, revealing that 1/I is gamma distributed with parameters I plus or minus equals nk, I squared equals y. The moments can be computed by taking the ratio, which shows that the mean plus or minus standard deviation estimate of the posterior distribution for I is. Generating gamma-distributed random variables, given the scaling property above, it is enough to generate gamma variables with I equals 1 as we can later convert to any value of I squared with simple division. Using the fact that a gamma, 1, 1, distribution is the same as an exp, 1, distribution, and noting the method of generating exponential variables, we conclude that if U is uniformly distributed on is distributed gamma, 1, 1, now, using the I plus or minus addition property of gamma distribution, we expand this result. Where UK are all uniformly distributed on for 0, I1 and apply the I plus or minus addition property once more. This is the most difficult part. Random generation of gamma variates is discussed in detail by de Vroy, noting that none are uniformly fast for all shape parameters. For small values of the shape parameter, the algorithms are often not valid. For arbitrary values of the shape parameter, one can apply the Arens and Dieter modified exponential rejection method algorithm GD, or transformation method when 0, k less than 1. Also see Cheng and Feast algorithm GKM3 or Marsaglia's squeeze method. The following is a version of the Arens-Dieter exponential rejection method. Let M be 1. Generate V3-MAR2. V3-MAR1 and V3M as independent uniformly distributed on 0, 1 variables. If, where, then go to step 4, else go to step 5. Let. Go to step 6. Let. If, then increment m and go to step 2. Assume I3/4 equals I3/4 m to be the realization of I1. A summary of this is: where is the integral part of k, I3/4 has been generated using the algorithm above with I equals k, who can be Euler distributed as explained above and are all independent. While the above approach is technically correct, de Vries notes that it is linear in the value of k and in general is not a good choice. Instead he recommends using either rejection-based or table-based methods, depending on context. Related distributions, special cases, conjugate prior. In Bayesian inference, the gamma distribution is the conjugate prior to many likelihood distributions, the Poisson, exponential, normal, para2, gamma with known shape I florin, inverse gamma with known shape parameter, and Gompertz with known scale parameter. The gamma distribution's conjugate prior is where Z is the normalizing constant, which has no closed-form solution. The posterior distribution can be found by updating the parameters as follows: where n is the number of observations, and xi is the ith observation. Compound gamma, if the shape parameter of the gamma distribution is known, but the inverse scale parameter is unknown, then a gamma distribution for the inverse scale forms a conjugate prior. The compound distribution, which results from integrating out the inverse scale, has a closed-form solution, known as the compound gamma distribution. Others, if x gamma, 1, I, then x has an exponential distribution with rate parameter I. If x gamma, I1/2/2, 2, then x is identical to I2, I1/2, the chi-squared distribution with I1/2 degrees of freedom. Conversely, if q to I2, I1/2 and c is a positive constant, then c_q gamma, I1/2/2, 2c. If k is an integer, the gamma distribution is an Lang distribution and is the probability distribution of the waiting time until the kth arrival in a one-dimensional Poisson process with intensity 1/I. If then if x has a Maxwell-Boltzmann distribution with parameter a, then if x gamma, k, I, then follows a generalized gamma distribution with parameters p equals 2, d equals 2k, and if x gamma, k, I, then 1/xinv gamma, k, I minus 1. If x gamma, I plus or minus, I, and y gamma, I squared, I, are independently distributed, then x/za plus a y, has a beta distribution with parameters I plus or minus and I squared. If xi gamma, I plus or minus I, 1, are independently distributed, then the vector, where xi equals x1 a plus a plus xn, follows a Dirichlet distribution with parameters I plus or minus 1, I plus or minus n. For large K, the gamma distribution converges to Gaussian distribution with mean I1/4 equals key invariance I2 florins equals key 2. The gamma distribution is the conjugate prior for the precision of the normal distribution with known mean. The Achat distribution is a multivariate generalization of the gamma distribution. The gamma distribution is a special case of the generalized gamma distribution, the generalized integer gamma distribution, and the generalized inverse Gaussian distribution. Among the discrete distributions, the negative binomial distribution is sometimes considered the discrete analog of the gamma distribution. Tweedy distributions The gamma distribution is a member of the family of Tweedy exponential dispersion models. Applications: the gamma distribution has been used to model the size of insurance claims and rainfalls. This means that aggregate insurance claims and the amount of rainfall accumulated in a reservoir are modeled by a gamma process. The gamma distribution is also used to model errors in multi-level Poisson regression models, because the combination of the Poisson distribution and a gamma distribution is a negative binomial distribution. In neuroscience, the gamma distribution is often used to describe the distribution of interspike intervals. Although in practice the gamma distribution often provides a good fit, there is no underlying biophysical motivation for using it. In bacterial gene expression, the copy number of a constitutively expressed protein often follows the gamma distribution, where the scale and shape parameter are, respectively, the mean number of bursts per cell cycle and the mean number of protein molecules produced by a single mRNA during its lifetime. In genomics, the gamma distribution was applied in peak calling step and chip-and-chip-seq data analysis. The gamma distribution is widely used as a conjugate prior in Bayesian statistics. It is the conjugate prior for the precision of a normal distribution. It is also the conjugate prior for the exponential distribution. Notes: see Hogg and Craig for an explicit motivation. Park, Sung Y. Bera, Anil K. Maximum entropy autoregressive conditional heteroscedasticity model. Journal of Econometrics, 219 230. Retrieved June 2, 2011 A. B. Papoulis, Pillai, Probability, Random Variables, and Stochastic Processes, 4th edition, Banayika BMSG, Ekanoic GEMUPD. A new point estimator for the median of gamma distribution. Viodayard J. Science, 1495 103, W. D. Penny, www. Phil-Ion UCL Lecoq Publications. Densities PSKL divergences of normal, gamma, Dirichlet, and Dirac densities, Minka, Thomas P. Estimating a gamma distribution. HTTP, Research Microsoft, Minka Gamma PDF, Choi, S.C. Wet, R. Maximum likelihood estimation of the parameters of the gamma distribution and their bias, Technometrics, 11, 4, 683 690, Luc Devroy. Non-uniform random variate generation. New York, Springer Verlag C. Chapter 9, Section 3, pages 401 428. Devroy, pages 406. A. B. Ahrens, J. H. and Dieter, U. Generating gamma variates by a modified rejection technique. Communications of the ACM, 25, 47 54. Algorithm GD, pages 53. Ahrens, J. H. Dieter, U. Computer methods for sampling from gamma, beta, Poisson and binomial distributions. Computing 12, 223 246 doi, 10.1007/BFO22931008. Site Sirax, 10.1.1.93.3828. Cheng, RCH, and Feast, GM. Some simple gamma variate generators. APPL. Stat 28, 290 295. Marsaglia, G. The squeeze method for generating gamma variates. Compart, Math. APPL 3, 321 325. Luc Devroy. Non-uniform random variate generation. New York, Springer Verlag C. Chapter 9, Section 3, pages 401 428. Think, D. 1995. A Compendium of Conjugate Priors. In Progress Report, Extension and Enhancement of Methods for Setting Data Quality Objectives, Dubey, Satya D. Compound Gamma, Beta and F Distributions. Metrica 16, 27 31 doi, 10.1007/BFO2613934, pages 43, Philip J. Boland, Statistical and Probabilistic Methods in Actuarial Science, Chapman and Hall 2007. Costa Rican colons, Aksoy, H. Use of gamma distribution in hydrological analysis, Turk J. Engine Environ Sci, 24, 419 428. J. G. Robson and J. B. Troy, Nature of the Maintained Discharge of Q, X, and Y retinal ganglion cells of the cat, J. Opt. Soc. Am. A4, 2301 2307, N. Friedman, L. Chi and XSI linking stochastic dynamics to population distribution, an analytical framework of gene expression, Viz. Reverend Let 97, 168302. D. J. Race, Mount Factiety and N. S. Baliga model-based deconvolution of genome-wide DNA binding, Bioinformatics, 24, 396 403, M. A. Mendoza Para, M. Nauka, W. Van Jewel, H. Granemia characterizing chip-seq binding patterns by model-based peak-shape deconvolution, BMC Genomics, 14834, references, R. V. Hogg and A. T. Craig Introduction to Mathematical Statistics, 4th edition. New York, Macmillan. P. G. Moschopoulos The Distribution of the Sum of Independent Gamma Random Variables, Annals of the Institute of Statistical Mathematics, 37, 541 Euro 544, AM Math-House Storage Capacity of a DAM with Gamma-type inputs, Annals of the Institute of Statistical Mathematics, 34, 591 Euro 597, External links, Haswinkel, Michiel, ed., Gamma Distribution, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Wallerstein, Eric W., Gamma Distribution. MathWorld. Engineering Statistics Handbook.